Suppose I took a piece of paper, very, very thin, and folded it over once. Then I folded it over twice. Folded it over thrice. Then folded it 4 times. And 5 times. As you can see, that stack is getting thicker and thicker and thicker. How thick do you suppose this stack would be if I were to fold it over 50 times? Would it be 2 feet, 5 feet, 10 feet, 50 feet? Maybe a mile? Actually, the height of the stack would be tall enough to reach the sun, which is 93 million miles away. Now, that on the surface sounds utterly absurd. But if you go to Module 2 and download the Excel spreadsheet entitled Exponential Growth, you'll see the proof. This phenomenon, where you start out with a little thin piece of paper and after 50 folds it's tall enough to reach the sun, that is known as exponential growth. And Einstein calls this the most powerful force in the universe. Now, Einstein ought to know a few things about forces in the universe. The most powerful force in the universe is exponential growth. Now, the financial application of this concept of exponential growth is known as the miracle of compounding. If you look at that Excel spreadsheet, you go down to the bottom, you will see a graph that monitors the height of the stack. And what you will find is in the initial phases, the first fold, second fold, third fold, 20th, 25th, 30th, 35th, that the size of the stack is remains very, very flat and doesn't grow very much at all. And at some point, around the 35th fold or something like that, it starts to turn up. And by the 40th, it's getting steeper. And then the 42nd, 43rd, 45th, 48th, 49th, that thing is almost vertical. And the size is growing, so fast it makes your head swim. That's the concept of exponential growth, or the so-called miracle of compounding. If you took some money and put it into an account, and you let the money in that account earn interest, and after a while, that interest would earn interest in subsequent periods, and then all of that interest would begin to earn more interest, and all of that interest would begin to earn more interest, etc., you are going to find a very, very similar phenomenon. It's known as compounding. At first, the amount of money in the account will grow very, very slowly, but then after a while, it starts to turn up, and then it turns up even steeper, and then you're off to the races. Now, keep in mind that when we folded the piece of paper over, let me fold it again, from the 5th to the 6th, what you see is that it doubles in size each time. When it doubles in size, that's the equivalent to a 100% rate of return. Now, nowhere I know are you going to get a 100% rate of return on investment. As a matter of fact, I got a brochure from a bank the other day that was very, very proud of the fact that they were going to offer me a 0.25% interest on a certificate of deposit if I deposited some incredibly large amount for an incredibly long period of time. 0.25%. That's nowhere near a 100%. So you can see that the function would remain flat for a much, much longer period of time. And when it started growing, it would grow at a very modest rate, and it would take a long time for the function to turn vertical. But you don't need a stack of dollar bills that would reach the sun in order to consider yourself rich or well off or even financially secure. So, if you put some money into an account, you let it grow, let it earn interest, that interest earn interest, and etc., you would like to know how much would be in that account at a specific point in the future. The mathematical concept that is used for computing this result is known as the time value of money. In computing this problem, you would start out with a given principle, which is the present value, and you would compute the amount that you would get in the future value. Or, suppose that you were to deposit, say, $100 or something like that into an account, and let it accumulate interest for a year. And then, at the beginning of a new year, you deposited another $100 into an account. And you let that earn interest for another year. And so, now you have the original principal, you have the interest, and you have the new deposit, the new payment, all earning more interest. And then at the beginning of another year, you put another $100 into an account. How much would you have at some point in the future? Here you would be starting with the present value, and you would be computing the future value of an annuity. The term annuity, of course, refers to yearly. In our first example, we were computing the future value of an amount, and in the second case, we are computing the future value of an annuity. Now, there are some situations where we actually work backwards, where we start with some amount in the future and bring it back to the present. Now, when we compute the future value, that is known as compounding. When we start with some future value and bring it back to the present, that is known as discounting. Here we start with some future value and compute the present value. Here there are two reasons why we would want to discount or compute the present value of some future amount. First is so that we can compute the real value of an amount. Of course, you know the way in which I'm using the term real. The real or purchasing power value of some amount. Naturally, because of inflation, when we receive money in the future, that's not going to buy as much as the same amount of money would buy today. The prices of goods and services are going to go up. So the trick in discounting is to select the appropriate discount rate. Now, that's not a problem when we compound, when we compute the future value of something. The compound rate is the interest rate or the rate of return or whatever growth rate it is. But when you discount, the trick is computing the appropriate discount rate. Now, when we're computing the real value of an amount that we will receive in the future, the purchasing power value of some amount that we will receive in the future expressed in terms of today's prices, the discount rate that we use, probably already obvious, is the rate of inflation. Now, we never know for sure what the rate of inflation is going to be because that rate of inflation is going to occur in the future. So we use what we anticipate to be the average annual rate of inflation. Now, there is a second reason why we would want to discount. The second reason is to figure out which is the better deal among two alternatives. A given amount of money received at some point in the future, or some larger amount of money received at some farther out time. Which of the two is better? The key is to compute the present value of these two amounts, and the guy with the highest present value is the better deal. Now, what do we use for the discount rate when we are comparing two alternative choices? It might seem intuitively obvious that we would still use the rate of inflation, because what we would want to do is to maximize the purchasing power value of the amount that we receive in the future. Well, that's intuitively correct, but this is ignoring the fact that you could take the amount that you received earlier and deposit it in some account and earn interest. So, an explanation of this is in the essay in the Module 2 section entitled The Required Rate of Return. In other words, the appropriate discount rate when we compare two amounts to be received in the future is something called the required rate of return. So read that little essay there, and it'll explain why we would use what the required rate of return is and why we would use that rather than the rate of inflation. So there are 4 different variations of time value of money formulas. First is to compute the future value of an amount, the future value of an annuity, the present value of an amount, and the present value of each of an annuity. Now, each of these have a slightly different formula, but rather than calling them formulas, I prefer to call them templates. So, if you're doing a time value of money problem, if you are able to identify the correct template to use, then you are 95% of the way home. Once you identify the correct template to use, all you need to do is to plug in the values into the variables that you know and solve for the unknown. And you can get some practice doing this with those 2 practice exercises, time value of money practice exercise and time value of money word problems, both of which are downloadable from the Module 2 section. And to identify what template to use in what case, read the essay entitled Uses of the Time Value of Money Calculations. So when you do that, you do the practice problems. If you have any questions about the practice problems, post questions and comments to the discussion board forum entitled Module 2. And we will see you on the discussion board.